Vectors and scalars are a way of representing measurements in physics that's crucial to understand whenever you're taking any physics course. So scalars are measurements that basically have only magnitude, while vectors have a magnitude, but they also have a direction, right? So let's take some examples. Some examples of vectors would be length, which is in meters, just around the length of 10 meters. Speed, which is in meters per second. We could say like 5 meters per second. On the other hand, vectors have to be represented with both a magnitude, so let's say 10 newtons for the force, rightwards. Or for example, with acceleration, we can say 15 meters per second squared at 15 degrees. When resolving vectors, it's always important to consider the axes. These axes aren't really there, but we can draw them or imagine them in order to help us resolve certain vectors or certain, for example, in mechanics, we would be resolving forces to draw a free body diagram. So even let's say we have the weight going downwards, then if we have a ramp, then maybe this would require us to actually draw a downwards component down the ramp, and then another leftwards component that goes perpendicular to the ramp. And this would be very key and very useful to drawing free body diagrams. So it's very important to know that you decide your own axes, and it doesn't have to be strictly vertical and horizontal. Anyways, in this situation, if we would like to resolve the horizontal force or the horizontal vector, and this horizontal vector binds the angle between it and the original vector, then we're going to use cosine. So we take the vector itself, the magnitude, and multiply it by the cosine of theta, and this will give us the horizontal vector A of h. And if you were to find the vertical component, which does not have the angle, then we would say, and this of course is a 90-degree angle, AV equals a cosine of 90 minus theta, just geometry, and this would be the same as saying a sine of theta, because cosine 90 minus theta is actually equal to theta. And these two rules are very important. We have both of them in the data booklet in the first section. Adding and subtracting vectors. So this is a nice question to represent what we call the head to tail method. The velocities Vx and Vy of two bolts, x and y, are shown. Which arrow represents the direction of vector Vx minus Vy? And actually I would like to also represent Vx plus Vy. So let's do this one first. So if we were to do Vx plus Vy, all we'd have to do is take the head of one arrow and then place it at the tail and then draw the rest of the arrow. Right? Now connecting these two arrows, we can take the shortest path, which would be this. So this is our resultant vector of Vx plus Vy. However, if we wanted to represent the scenario in the question, we would just have to simply reverse the arrow with the negative sign. So reverse Vy. Let's put the tip of Vy here and then draw it, and then we would have to reverse the tip to be at the other end of the arrow here. So these two vertically and horizontally cancel out, and what we're left with is just this rightwards velocity, and our answer here would be D, that these Vx minus Vy would just point rightwards. This is another example of paper 1 where we'd actually need to use vectors, and it states that the magnitude of the resultant of two forces acting on a body is 12 newtons. So we want to find the pair of forces that can possibly contribute to these 12 newtons. So if we have 1 and 2 newtons, even if they were to go in the same direction, like this, then our maximum would be 3 newtons. And if you have 1 and 14, then our minimum force would be if 1 was going leftwards, and then the 14 was going rightwards. And that would be 13 newtons. And if you have our 5 and 6, if you have 5 going to the right, and then 6 going to the right, then that would only equal 11 newtons. So D must be our answer, where some combination with an angle of these two would actually give us a net force of 12 newtons, because this is the only possible combination out of these four.